All right, let's start, we guess. Not many people, but let's do this. Okay. All right, so the original plan for today was we go through the vesting contract and some related changes we did to the governance module. But there are two things regarding the airdrop contract, which we went through last time that I didn't cover. So the first thing is we made a change. So if you remember, we had a claim deadline where if the deadline is passed, we have a callback function that anyone can call to claim to call back the tokens into the community pool. So the decision was made that we don't want such a deadline. We want the claim to be indefinite. So as you can see, I removed the claim period parameter from the instantiate message. And I removed the callback function from the execute message. So what I did to call back was I moved it to another message type called pseudo message. So if you don't know, pseudo stands for super user do. It stands for actions that only certain privileged users like the system administrator can call, right? So in the context of Cosmosm contracts, pseudo message are messages that can only callable by the L1 governance module. So let's take a look at contract.rs. What we have here is, in addition to the instantiate endpoint, execute endpoint, we have a pseudo endpoint. So what's the deal with pseudo? Well, if you go to look at the, let me check something. I have Cosmos SDK somewhere. Here it is. Wait a second. Add a folder to workspace. Cosmos SDK. All right, so if you go to take a look at the Cosmos SDK message type. Oh no, I mean there wasn't this that not Cosmos SDK. Give me a second. All right, so if you look at the available message types available in the Cosmos module, you see we have instantiates, which corresponding to the instantiation and entry points, execute, which corresponding to the execute entry points, migrate, the migrate entry points. There's no pseudo entry point, and that's intended because functions in this entry point are not supposed to be callable by users or other contracts. They are only supposed to be callable by the governance module. So where is that? Where that is in this protobuf file. So these are data that the governance module can make use of. So we have store code and instantiate. So these are useful if your blockchain is has permission contracts, right? So if you don't want anyone to be able to, you don't want everybody to be deploying contracts as they like. You can limit your contract deployment power to the governance module, and they have to do it via governance proposals. Same with migrate, and there is the pseudo contract proposal, right? So you create a governance proposal with a title, description, the contract address you want to interact with, and your pseudo message. So basically, that's how it works. So in this governance gated callback function, we don't check the deadline because there's no deadline. We just query the total amount of coins held by this contract, and we just send it back to the community pool the same way as we did before. All right, so this is the change we made. And the second thing with airdrop contract is I realized I did not show you guys this contract in action. So I think it should be really helpful if I spin up an actual blockchain and let the blockchain run and interact with the contract to show you guys how it works. So that's exactly what we're going to do today. All right, so So let's do this. So the first thing to set up a blockchain is to compile the blockchain code. So I'm currently in the hub repository. So if you go to hub and take a look at this file called makefile, this file defines basically a bunch of shortcut commands, right? So these two commands are for compiling our chain client. So this is one that we're going to use. So but if we type make install in our console, it will basically run this command. And it will also pass in a bunch of flags into Go, which we have a bunch of code here to construct these flags. So if you're interested, you can take a look at them. But what we are going to do is we are going to make install. So this is basically they're compiling the chain and installing the binary basically. It shouldn't take too long. So we're going to see a bunch of warning messages. These are basically related to Mac OS. So if you're on Linux, you should not see this. It's fine. These things doesn't really interfere with our the normal working of blockchain. Yeah, hopefully, please. All right, so installation is completed, and we can run the command marsd version to check that the marsd version to make sure that it is installed properly. Currently, it's empty because I have not tagged a release yet for our chain. So so the version only shows up if you do git tag, for example, v1.0.0. If you do this, it will have a version, but I don't have a version yet, so it's empty. But we can check it via marsd version long, where it will show more info, like our Cosmos SDK version, our dependencies version, the Go language version, our build flags, which are constructed by that bunch of code, our latest git commit. So yeah, so this is how you can check whether your installation is complete. So the second step, which if you have attended my validator workshop, you already know, which is to create a genesis state. So we do that by marsd init, the name of your node, in which case it's my name, and the chain ID, which is the name of the chain. So I have already done this. So once you do this, it will generate a file called in your home folder called .mars. And inside that is going to be a config directory where you have a bunch of very important files, config, app. You can check these. You can check out my validator workshop on what this means. But what matters here is the genesis.json. So this is our genesis state. So I have already have the genesis file open here. So as you can see, this JSON object is the most important one. It basically defines the genesis state of every Cosmos module. So first we have the auth module, which stores all the available accounts. So for example, this one is my validator account. This is my dev account. This is a so-called public account, which we're going to talk about shortly. We have the OSD, we're going to skip that bank module, which we have the token balances of each account. So we have the Mars token and the test token, etc., etc. So what really matters here? Oh, well, here's another important one. Here are where we register our validators. So yeah, we have one Genesis validator in this case. Okay, so what really matters, what matters most in our context is the WASM module. So if you go to my hub periphery repository, I have a script here called Pseudomessages, which deals with this part. But here's the result of the gen messages. So basically, we have an array of messages enclosed by these square brackets. So the first message, we upload the vesting contract. The second, we upload the airdrop contract. So you see this bunch of stuff are literally the binary code of the contracts. And then we instantiate these contracts. So this one is for vesting, which we talk about later, and this one is for airdrop. Well, this one is set up vesting positions for each Mars contributor. So in this case, we only have one contributor, myself. So that's one. And in this step, we transfer the ownership of the vesting contract from me, the developer, to the governance module. So we'll talk about this later. Here, we instantiate the airdrop contract, right? So we upload the Merkle root, and we no longer need a clean period. All right, so it formats my, I have an auto formatter formatting my file. So anyways, yeah, so we upload the Merkle root and we send the appropriate amount of funds to the contract. So the Genesis file is ready. You can run this command marsd genesis validate Genesis. Hopefully it tells you it is valid, which is great. So now we can start the chain, but first step is we want to, because I had run the same blockchain before, so I want to clear my local storage. So we start freshly from a new. So the command for that is marsd tendermint unsafe reset all. We want to specify the home folder, and we do marsd start. Right. Right. So when we compiled marsd, I forgot to mention there is a build flag. So we can use different databases behind the scene. So by default, we use a database developed by Google called LevelDB. So this is the same database that literally every other chain uses. Like Ethereum uses LevelDB, Cosmos by default uses LevelDB, Avalanche too, I think. So, but you can also specify to use alternative databases. For example, there's the C LevelDB. So that's LevelDB, but implemented in the C language. Or you can use RuxDB. So RuxDB is a pretty high performance database backend. It seems to be tremendously more efficient in running the chain compared to LevelDB, but it is quite experimental. So here we make it an optional parameter. I previously compiled the chain with LevelDB, with RuxDB, so that's why we see an error here. But we can change our configuration. So this is in config tomo, where we select the database backend and have a RuxDB here. So I want to change this back to LevelDB, and specifically the Go language implementation of LevelDB. So Go LevelDB. So let's do the same thing once these starts, and that should work. Yeah. So let's wait for the first block. That's our first block. So now we can try interacting with our contract. So I spin up a new terminal. And this is the latest status of our chain. Let's format a little bit. So we are currently on block 5. My validator has this much voting power. So yeah, that's our Mars chain. So let's do query. Wasm list contracts 2. Yeah, so we want to know what's the address of our airdrop contract. So I already know the code ID is 2 because it is the second code I uploaded, if you remember in the Genesis file. So yeah, so this lists all contracts instantiated based on code ID number 2. So this is our airdrop contract. So let's try query the contract first. So marsd query wasm contract state. And there are two types of queries, smart query and raw query. So we want to do smart query. So we want to have the contract address and our query message encoded in JSON. So let's try query config first. And that returns our config state, which is our Merkle root, which if we look back at the code, it corresponding to the config response, which is equal to instantiate message. So this is our response, and in this case, it is parsed into the TOML text format. So if you prefer JSON, you can do this. Output JSON, yeah. So that is our instantiate message here. Right. So let's try claim our airdrop, shall we? So I have a few helper scripts here. So build Merkle tree and send message. So let's remember which parameters we need. We need Terra accounts, Mars accounts, the amount, the proof, the signature. So let's take a look at these few helper scripts. So let's claim for this guy, right? The third account, Terra 1757, and the amount entitled by this amount is 420.69. So let's run this first helper script I've prepared. So as you can see, these scripts are for testing. Basically, I generate a few test cases. So these two are invalid test cases. The first one is the valid test case. So this is our Merkle root, A7BA, which is the one we put on the blockchain. So this is our Merkle proof. This is our Terra address. And let's run the second script. What's that? Run file, second script. This is our Terra public key. This is the Terra address, and this is the corresponding Mars address. So let's do this. Let's interact with the contract. marsd transaction wasm. And here you can select your entry point, which is execute. So wasm execute. Let's see what are the arguments that's required. We need the contract address, our JSON execute message, the amount of coins we optionally want to provide into the contract. So our contract address is this. Our JSON execute message, which is claim, within which we need to provide a few arguments, a few parameters. And that first we start with our Terra public key, Terra account pub key. And for that, we go up and copy that from here. This is our pub key. And our Mars account, which we want to use to receive the airdrop, which we also go up to this address. The third thing is the amount. So amount is 420.69. Let's do signature first. Which we also go up and copy here. This is our signature. And the proof. So that's going to be an array. So this array has 3 elements. Let's copy them into here. one by one. Right. So we do not need to pass any coin into this contract for this execution. So we're going to skip that. And we are going to specify which account this transaction shall be originated from. In our case of the airdrop, the airdrop this execution does not have to be invoked by the user themselves. It can be invoked by anyone because the signature already proves that the user has authorized this transaction, right? So here I'm going to use my dev account to invoke it. And I'm going to let the chain estimate how many gas I want to use. And I'm going to use another parameter called gas adjustment. So this is necessary because the estimation of gas is not necessarily accurate. So if I execute, well, this is going to take 100 gas. When the transaction actually gets executed on chain, it might take a little bit more, a little bit less. There's some randomness, right? So this multiplier, what it does is basically, let's say the estimation is 100 gas, my multiplier is 1.4, then we are actually going to use 140 gas. We're going to request based on this multiplier. So yeah, so that's the use of it. So the gas prices, which is 0, right? So yeah, so that is our execution message, and hopefully it works. My password, and it does not work. And the reason for that is the proof is invalid for some reason. Let's see. First 3E1 is 37. The last one I copied wrong. So last one. So the last one I copied it from an invalid test case. So that's right. So that's our contract working as intended, rejecting false proofs. Hopefully this works. And that works. So let's submit the transaction. So this is our transaction hash. We wait for a block for it to be confirmed. There it goes. So let's query this transaction. Yeah, so this is our transaction. It is formatted in the tonal format, which I don't quite like. So I'm going to have it output to JSON instead. So yeah, so this is it. Let's look at the transaction log, right? So this is our execute message, and the log is outputted here. And as you can see, it outputs an event, right? Which is defined here, right? So we have this event called Mars airdrop claimed, have 3 keys, 3 attributes. And this is our event. It's prefixed with wasm hyphen. So that is just how wasm module works. And our three attributes. So it's working as intended. So let's query the bank module to see if the recipient actually received the coins, right? So marsd query bank balances, and the recipient Mars address, and it does have 420 and 69 UMARS, right? So that's working as intended. That's great. So I just showed you guys the claim function. And now I'm going to show you guys the callback function, how to create a governance pool to execute the callback. But before we do that, is there any questions on this so far? No? Okay, let's move on. All right, so let me check something first. in the Genesis file, let's take a look at the governance module. Up here. Right, so deposit period is 5 minutes, voting period is 5 minutes. That's great. We don't want to wait for a 7 days voting period, right? So let's do 5 minutes. Okay, so we want to do Mars D transaction. We want to do gov and submit proposal. Let's see. So we have a few options for proposals. One of them is pseudo contract. This is what we are going for. So these are all the so-called governance hooks or governance handler types, which is, as you remember, is defined as a protobuf right here. Proposal, right? So we have instantiate proposal, store proposal, execute proposal, pseudo proposal, update admin, clear admin, pin code and unpin code, for which we have them respectively here. We also have a few from other modules, like this is the IBC module, this is the param module. And these things are hooked up basically in the app.go file in the client. So here I have a helper function which adds all the governance routes. So this is the gov module route, the param module, distribution module, upgrade module, IBC module, WASM module. So and when we instantiate the gov router, gov keeper, we pass in this helper function. So this is how we created these, basically these commands inside our chain. So let's do this now. We want to do pseudo contract. See the help. Pseudo contract. So we need to specify the contract address and the JSON pseudo message. It says migration argument. I'm not quite sure why. It should be pseudo arguments. How is the SDK message is connected with the smart contract endpoint? So that is handled by the WASM module. So when you first send your the, let's say, the execute message to the chain, the message is dispatched to the WASM module. So let's say you execute. So this is what the WASM module will receive. It will receive who you are, which contract it is, what is your JSON execute message, and what are the found. So the chain will tell the WASM module these data, and the WASM module will look at, hey, this is an execute message, so I need to dispatch this message and funds to the execute endpoint entry point of this contract, and it will just do it. Right? Maybe I can show you where it does it. Message is defining the keeper in the message dispatcher file. I think I'm actually not very sure. So in execute contract, we do this. Right? Well, I guess I'll leave it to you to explore this, but yeah, basically that's how it works. Yeah, so pseudo contract, let's specify the contract address, which I don't remember. This is the contract address. And our message is just callback. There's no parameter, right? From dev, gas is auto, gas adjustment 1.4, gas prices is 0. Invalid proposal content. That's because we need to specify the title and description, right? Title is callback. Description is blah. This should work. And that works. All right, our proposal is submitted. Let's wait for one block for it to confirm. There it goes. So let's, I forgot to deposit. Let's see. Mars D query gov proposal number 1. So this first ever proposal is number 1. And we can see it is in the, its current status is proposal deposit period because we didn't make any deposit. But anyways, here's our content of the proposal, which, if you remember, is defined here at pseudo-message proposal. We have a title, a description, a contract, and a nice message. And we have title, description, contract, and the message. Yeah. So let's make the deposit now. And the minimum deposit is, as I defined in the Genesis state, is 10 Mars. So let's do that. Mars the transaction gov deposit 1. This is our proposal ID, and I want to do this many new Mars from dev gas auto gas adjustment 1.4. I don't have to specify gas prices if it's 0. It's 0 by default. So submitted. Let's wait for one block. There we go. Let's query the proposal again, and you can see it is currently entering the voting period because we have made the minimum deposit, so it's currently voting. And the voting period ends in about 4 minutes, so let's do it. Mars the transaction gov vote. Well, we specify the proposal ID and the option. Well, 1 option is yes. Dev gas auto gas adjustment 1.4. Submitted. Well, one block. So let's query our vote at RC query gov vote. We provide the proposal ID and our address, and you can see we voted yes. All right, so we have voted. Now we just need to wait for 3.5 minutes for the poll for the voting periods to finish, and then we see how it works. So before we wait for that, let's do something. Let's query. Let's see how much found currently there are in the distribution module. So you can see currently the distribution the community pool is empty, right? So after the pool has passed and the poll executed, it should receive all those tokens here, right? And also let's query how much funds that is currently held by the contract. For that, I need to find the contract address. Contract address here. So Mars D query bank balances. So the contract currently holds this much Mars tokens. So at the end of the poll, which are in 2.5 minutes, these tokens should have been transferred to the community pool. So let's take a rest. Let me drink some water, and let's wait for the poll to finish. This time, 2 minutes. All right, 30 seconds. Ten seconds. Right, in 2 blocks, it should be executed. One. There we go. It should have been executed. Let's see. It's rejected. That's because we forgot to vote with the vesting accounts. So that's actually what I was about to talk today. So I forgot to vote with the validator and the vesting account. So it didn't meet quorum or threshold. That's my mistake. So I voted with the wrong account because my dev account actually did not have any stake. My validator has 100% of the stake. So we have to vote with the validator as well, right? So let's do this again. I'm really sorry about this. So but we have to do this again. Let's try submit the same proposal, but this time let's do the deposit. There it is. All right, so we made the deposit. Proposal number 2 is currently voting, so let's vote. Let's first vote from our dev account. Okay. Vote for proposal 2. And we have to vote with our validator account as well. Okay. All right, so now in about 4 minutes, it should work. But let's not waste 4 minutes. Let's enter the next topic while we're waiting, which is our vesting contracts. So let's take a look at our vesting contract now. Okay. So in our instantiate message, we have the owner. So owner is the account that can create vesting positions. So we specify owner at the beginning. And we have an schedule. So let's take a look at this picture here. This shows how schedule works. So each schedule has 3 parameters: the starting time, the cliff, and the duration. The way it works is between start time and the end time. So end time is start time plus duration. The vesting goes linearly from beginning to the end. However, before the cliff time, right, it is set to 0. So after the cliff, it goes up and do it linearly. So as it shows here. And for each account, we have 2 schedules. One is called the vesting schedule, and the other is called the unlocking schedule. So vesting schedule is personalized to each developer. Unlocking schedule is defined by whatever time the protocol is launched. So it is the same for everybody. And at any time for a particular contributor, the amount of Mars tokens they can withdraw at that time is the available amount according to the vesting schedule, or the withdrawable amount according to the unlocking schedule, whichever is smaller, minus the amount they have already withdrawn at that point, prior to that point. right? So the smaller one minus already withdrawn. So that is the algorithm. Why do we have to have two schedule, and why does the schedule needs to work this way? That is because our lawyers taught me to do this. So that's the reason. We just listen to lawyers. So yeah, we instantiate, and once we have instantiated, we call this function, the owner needs to call this function create position for each of the Mars contributors. Just repeatedly call this one. Once done, the owner will transfer the ownership to the governance module so that no more positions can be created. And at any time, the contributor, the recipient of the tokens can call withdraw to withdraw their amount. We have a few query messages, the config of obviously, and the position. So position, we are going to return these data. So the address of the user, the amount of token allocated, the amount of token that has been vested, the amount of token that has been unlocked, the amount that has already been withdrawn, the withdrawable amount, which is these two, whichever is smaller, minus this, and the schedule. So, yeah. For voting power, which I think we're going to talk about in the next session, are used by the governance module to calculate your voting power, because we want these contributors who have tokens locked in investing also being able to vote. So we modified governance module to count the locked voting power into the calculation of voting power. Yeah. So I think we don't have enough time for this today. We can do this next week. So yeah, that's the message. But let's go back and take a look at our governance proposal. And it is passed. That's excellent. So let's take a look at our community pool, and indeed it has received the appropriate amount of tokens. And if we query the balance of our contract, it is 0. So that's brilliant. That worked as intended, right? So the funds have been clawed back. That's great. Any questions on this regarding governance, regarding clawback, regarding the vesting messages, anything? No? All right, so I think we have about 10 something minutes left. I don't want this session to go on forever. Let's keep it under 1 hour. So let's quickly take a look at this. So in the state, we save the owner, we save the unlock schedule. So reminder, unlock schedule is the same for everybody. Vesting schedule is customized for everyone. So for each contributor, we save the total amount, the amount already withdrawn, and their personalized vesting schedule. So yeah, that's instantiation. We just save these two things. So in our first execute function, the create position, we first make sure that the only owner can call this function. Then we parse we parse the received coins. So the owner, in addition to call this function, also must send the appropriate amount of Mars tokens to get along with the message. So we make sure that only one coin is sent. The coin must be Mars token, not anything else, and the amount must be greater than 0. So we make sure these things, and if yes, we update the position. So for each position, we make sure that a position does not already exist for this user first. So if the user already has a position saved, we are not going to override that. If not, then we save the total amount, which is the amount of Mars tokens sent by the owner. We save the vesting schedule, and we initialize the withdrawn amount to 0. And we create a event. And that's it, very straightforward. So if we call withdraw, we load the unlocking schedule and the user's position, and we call this function to compute how much tokens we can withdraw, right? If the amount is 0, we're going to throw an error. If the amount is not 0, we're going to update the withdrawn amount in the position and save that. And then we dispatch a bank send message to send the withdrawable amount to the user. So yeah, that's it. For transfer ownership, we make sure only the owner can transfer ownership, and we save the address of the new owner. Very straightforward, right? So the only part a bit complicated is this function where we actually compute the withdrawable amount. So let's take a look at that. So as a reminder, this is our schedule. Before the cliff time, your withdrawable amount is strictly 0. Before the end time, your withdrawable amount is strictly the total amount. Between these 2 points, it is vested linearly. So this is what we do here. Before the cliff, it's 0. Before the end, after the end, it is the total amount. During the period, it is vested linearly. So it is the time that has passed in proportion to the duration, right? So we compute the vested amount according to the vest schedule. We compute the unlocked amount according to the unlocking schedule. We take the minimum between these two, and we subtract the amount that has already been withdrawn. So this is our withdrawable amount, and we return these 3 numbers. So in the withdraw execute function, we only care about the withdraw, so we don't take the other 2. We take the withdrawable amount, and we send the user this amount. In the query function, we grab all 3 values and we compose them into this response object, right? So in addition to this query message, where we only query that for a single user, I also have another query function which queries all users, right? So we have these pagination parameter, which we talked about that in last session about airdrop. So we have start after limit. So we enumerate the position map. So position is a map. The key is the address, and the value is this position structure. We enumerate that. We take the limit amount, and for each of these things, we grab the user address. But this is voting power. We compute the response, and we collect that into a vector and return that. So this function is here. Remember, we compose this response item. So I think that's about it. We're 53 minutes in this session. I think I'm going to call it a day here. So next week at the same time, we are going to talk about voting power, the voting power queries, and the modifications we made to the hub contract, where in the governance we modified the vote tallying logic. And specifically, I'm going to show you how do we query WASM contracts from the SDK module. This is right here, right? We query the contracts inside our Gulf module. So yeah, I think that's for today. If you don't have any questions, feel free to leave. If any questions, feel free to ask in the chat or just join the voice channel. But other than that, that's it for today. Yeah, thank you for joining. Yeah, and we can shut down the blockchain. Yep. All right, I'm gonna jump off now since there's no question, and I wish you all have a good day.